electromagnetic wave. After that introduction, you will be able to understand all new topics. So see, electromagnetic wave is a type of wave which does not require any medium to propagate. This electromagnetic wave consists of electric field. It consists of magnetic field. Electric and magnetic field we already know. Electric and magnetic field in electromagnetic wave is perpendicular to each other. So your electric field is along y-axis, your magnetic field is along z-axis, and your wave is moving along x-axis. This is electromagnetic wave. I'm repeating it again. Electromagnetic wave is a type of wave which does not require any medium to propagate. It can even travel through vacuum. It consists of electric field and magnetic field. Both electric and magnetic fields are perpendicular to each other. They are also perpendicular to the direction of propagation of wave. That's E wave. So those who were absent in the last class, Amalia, Ahmed, Sania, is it clear what is electromagnetic wave?
Yes, sir.
So Amalia, can you just brief what is electromagnetic wave?
Electromagnetic waves does not require any medium, but can travel through vacuum.
Okay. And
It consists of both electric field and magnetic field.
and both electric and magnetic fields are perpendicular to each other, right? They are perpendicular to each other and also to the, it is perpendicular to the direction of propagation. So that this is what we have already discussed. Okay, after EM wave, we need some properties of electromagnet. Okay, this topic is almost independent of the last lecture. So Shahzada, just try to understand. Huh?
Okay, sir.
So you understand what is electromagnetic wave, Shahzada?
Yes, sir, a little bit.
Yes, did you get what is electromagnetic wave?
Yes, sir.
Can you just summarize?
Like, sir,
It does not require any medium to propagate, right?
yes, sir, it does not
First
require
thing.
any.
And it consists of electric and magnetic field. Okay,
Yes, sir.
that's electromagnetic wave. And how those, and what are the directions of those electric and magnetic field?
It's a perpendicular.
Perpendicular. So that's electromagnetic. So the first property of electromagnetic wave is it's transverse in nature. Transverse in nature means electric, magnetic field and direction of propagation are mutually perpendicular. So if electric, magnetic field and direction of propagation are mutually perpendicular, then we call that your electromagnetic wave is transverse in nature. The second property is if you take the ratio of electric and magnetic field, the ratio of electric and magnetic field will give you the speed of light. So the ratio of electric field and magnetic field is equal to the speed of light, and speed of light is 3 into 10 raised to the power 8 meter per second. That's the second property. Okay, does electric field have energy, Noor?
Yes, sir.
Does electric field have energy?
Yes, sir, it has.
How will you, and do you remember any expression for that energy? Yes, Noor. Can you think of an expression for that energy? Abdullah, do you remember any expression for energy of EM wave? No. Mariam, do you remember any expression? We did this expression in capacity. See, The energy,
So half E naught.
yes, half epsilon naught E square. See. Okay, before starting that energy, just one more expression. The speed of electromagnetic wave. In vacuum, the speed of electromagnetic wave is 1 by root over mu naught and epsilon naught. Do you remember what is mu naught, Mariam? Mariam will tell. Mariam, do you remember what is mu naught? This mu naught. We did this mu naught in magnetics. No. Fatma, do you remember what is this mu naught?
Relative permeability.
And you remember the value of this term? Absolute permeability, 4 pi into 10 raised power minus 7. And what is epsilon naught? Absolute permittivity of free space. And what was its value? Sania, do you remember the value of epsilon naught we did in electrostat Coulomb's law? Sania, I can't hear you. Sania, your mic is not working properly. Ahmed, do you remember the value of epsilon naught?
Epsilon naught or mu naught? Epsilon naught.
Epsilon.
Yes, it should be 8.85 into 10 to the power minus 12, I guess.
Right, Abdullah, look at 8.85 into 10 raised to minus 12. So if you want to calculate the speed of electromagnetic wave in vacuum its speed is 1 by root over mu naught epsilon naught. Mu, we know that this is 4 pi into 10 raised to minus 7. And epsilon naught is 8.85 into 10 raised to minus 7. So when you work it out, the whole thing, it comes out to be 3 into 10 raised power 8 meter per second. This is the speed of electromagnetic wave in vacuum, 3 into 10 raised power 8 meter per second. If you do the same calculation in medium, instead of mu naught, we use mu. Instead of epsilon naught, we use epsilon. Mu is relative permeability into mu naught. In the same way, epsilon is epsilon r into epsilon, relative permeability. This 1 by mu naught epsilon naught, you can write this whole thing as C. So that's C by root over mu r epsilon r. So that is the speed of electromagnetic wave in a medium. And this is the speed of electromagnetic wave in vacuum. And this term, root over mu r epsilon r, this is known as the refractive index. This is the definition of refractive index: relative permittivity and relative permeability. The product of relative permittivity and relative permeability is known as the refractive index. Then there is this another property that all optical phenomena in nature are due to electric field vector. There is no role of magnetic field vector in optical phenomena. Okay, can you name some optical phenomena?
Refraction.
Refraction, good. Another?
Reflection.
Reflection, dispersion. All these optical phenomena are due to electric field vectors only. There is no role of any magnetic field vector in optical phenomena. That's sixth equation. Okay, just note it down, then we'll do a few more properties. Shazada, is it clear, these properties? Yes, no, whole diffraction interference are due to electric vectors only.
Okay, sir.
Yes, written. Can I scroll it?
Yes, sir.
Sania, is it clear?
Yes, sir.
Now your mic is full. Sania, can you just, by looking at the property number 3 and property number 4, can you decide where is the speed of light maximum? It's maximum in vacuum or it's maximum in medium?
Oh, sir, in vacuum.
In vacuum. How you decide that it is more in vacuum than in medium?
I don't know, sir.
Right. It was a guess, intelligent guess, huh? See, Sania, see, in medium, the speed of light is c divided by something. Speed of light, c is speed of light in vacuum divided by something. So we're getting v, which is c by something. When you divide c by something, the value will decrease, right? It will be smaller value.
Yes, sir.
Like if I tell you divide 4 by 3, obviously 4 by 3 is less than 4. So dividing c by something. So this whole fraction is less than b. It's less than c.
So what's the definition of refractive index?
Refractive index, there are two definitions of refractive index. One is the ratio of speed of light in vacuum to the speed of light in medium. This definition will do in diffraction. Refractive index can also be defined as its root over relative permittivity and relative permeability. The product of relative permittivity and relative permeability.
Okay, sir.
But the definition that we usually use in optics is the ratio of speed of light in vacuum to the speed of light in medium. That's it. Okay, so can I scroll it?
Yes, sir.
Okay, so electric field have some energy. Magnetic field also have some energy. So from here, you can conclude that electromagnetic wave should have some energy. So the total energy of electromagnetic wave or the total energy in electromagnetic wave have two contributions. One contribution is from electric field. Another contribution is from magnetic field. So I should write it again. So see, the energy density carried by EM wave. I should write these things. This will be seventh property, right? I need energy density of EM wave. Energy density for EM wave. So this energy density for EM wave will have two contributions. One contribution will be from electric field. So it will have two contributions. One is from electric field. And from where the second contribution will come from?
Magnetic field.
Second contribution will be from magnetic field. So first let's see what is the contribution from the electric field. You can say that the contribution from electric field is known as electric energy density. Okay, what is energy density first of all? Do you remember what do you mean by energy density? What's the meaning of energy density? Does anyone
Energy per unit volume.
Energy per unit volume. Energy density is energy per unit volume. So electric energy density means contribution of energy from electric field only. And we write this energy density in this way. This is half epsilon naught E square. This is electric energy density. And remember here, E means ERMS. Does anyone remember the relation between RMS value and the peak value? Anyone?
Peak value
ERMS is E naught by root 2.
707.
Yes, ERMS is E naught by root 2 or 0.707. So instead of this E, you can, if you want, you can even substitute this E naught. So your UE will comes out to be, that's half into epsilon naught into E, which is E naught over root 2 whole square. So it comes out to be half epsilon naught E naught square by 2. So that comes out to be 1 by 4 epsilon naught E naught square. So this is the electric energy density in EM wave. 1 by 4 epsilon naught into E naught square. Or when you write half epsilon naught into E square, that means this is the RMS field. And the E naught means the peak value of field. Peak value of electric. Note it down. Then we will see the contribution from the magnetic field. Is it clear, everyone?
Yes, sir.
Shahzada, is it clear, this electric energy density?
Yes, sir.
Noted.
Yes, sir.
So that was electric energy density. Amalia, what should be the next type of energy density in this system? In electromagnetic wave? Yes, Amalia. Which energy density this should have else than electric energy density? Maria? Else than electric energy density, what type of energy density the EM wave should have? Mariam? Abdullah, what should be another type of energy density in electromagnetic wave?
Magnetic energy density.
Magnetic energy density. Yes, magnetic. Right, Mariam. Magnetic energy density. See, we write magnetic energy density as UV. And magnetic energy density is half B square divided by mu naught. This is the magnetic energy density, which is B square by 2B naught. This is magnetic energy density in electromagnetic wave. This B is again the RMS value. B is again the RMS value of magnetic field. It is the RMS value. Sania, what's the relation between the RMS value and the peak value? Sania, do you remember any relation between RMS value and peak value?
Yes, sir. V is equal to root 2. V0 by root 2.
B naught. So what we can do is, instead of this B, we can substitute this B naught there. So when you do this substitution, the magnetic energy density will comes out to be half. It's B naught over root 2 square into 1 by mu naught. So that's B naught square by 4 mu naught. This is magnetic energy density in EM wave. B naught square by 4. So you should remember this thing. If you are using half B square by mu naught, that means you are using the RMS value. But if you are using B naught square by 4 mu naught, that means this is the peak value of the magnet. Note it down. Yes, noted.
Yes, sir.
So Abdullah, how will you calculate the total energy density? What if I need total energy density?
We're adding them vectorically.
The total energy density will be the sum of electric energy density plus magnetic energy. That's the total energy density.
So vectorically or scalar?
Energy is a scalar or a vector?
Yes, yes, scalar.
Scalar. So scalar addition. Half epsilon naught E square plus half B square by V. Now, next. There's another important thing which says that electric energy density is exactly equal to magnetic energy density. This you should remember. You can even prove that you can start with electric energy density and you can convert it to magnetic energy density. Both comes out to be equal. You should always remember that in an electromagnetic wave, you get equal contributions from electric field and magnetic field. 50% contribution is from electric field, then another 50% contribution will be from magnetic field. This is it. Note it down. Now this you have written, write this total energy density. Then we'll do some numericals. Yeah, that may be the question. Yes, can be asked. See, it's a straightforward calculation. If you want me to prove it, see. U is half epsilon naught E square. Okay. Okay, first of all, write it down, then I'll prove it. The 2-3 step calculation. See, we just have to prove that UE is equal to U. Let's call this as equation number 1. Do you remember any relation between EB and speed of light, Noor?
E by B is equal to C.
E by B is equal to C. So from here, you can write that E is equal to C. You can write E is equal to C. That's second equation. So instead of E, you can substitute CB. So, Mariam, do you remember any relation between speed of light, epsilon naught, and mu naught? Mariam. No, we just have done it. Amalia, do you remember any relation between C, epsilon naught, and mu naught?
C is equal to E naught by V naught.
No. This is already we have written. I'm asking epsilon naught permittivity, absolute permittivity, and absolute permeability. You just have written.
C is equal to 1 by root mu naught by mu naught into E.
Right, this is 1 by so mu naught into epsilon naught. This is the relation. Next, what we can do is we can take square on both the sides. So we'll get C square is 1 by mu naught into epsilon naught. Or you can write that epsilon naught is 1 by mu naught into C square. I call this as equation number 3 now. Now what we can do is we can substitute 2 and 3 in 1. So when we substitute 2 and 3 in 1, we get electric energy density as half epsilon naught, which is 1 by mu naught c square into E square, which is C square into V square. So C square gets cancelled out with C square. So this is V square by 2V naught. So this is electric energy density, which comes out to be equal to magnetic energy density. So this is how we can prove that electric energy density and magnetic energy density are equal. Is this proof clear for everyone?
Yes, sir.
Okay.
Yes, sir.
Note it down. Ajay, noted?
Yes.
After this energy density, there are two more definitions. The next is momentum of Vmware. Momentum of Vmware. So along with energy, this EMF also carries some momentum. That momentum can be written as its total energy divided by the speed of light. This U is total energy. And the C is speed of light. If you know momentum, then you can calculate force. Force is change in momentum by time. So you can write that force is P by T. Use this expression if surface is absorbing. If you have an absorbing surface. If you have an absorbing surface. But if you have a reflecting surface, what type of surface is mirror? Is it a surface which absorbs or it's a reflecting surface?
Reflecting.
If you have a reflecting surface, then force is 2P by T. Reflecting surface. So remember this thing. If you have an absorbing surface, then your force is P by T. But if your surface is purely reflecting, then your force is 2P by T. This is for the reflecting surface.
So T is
Momentum.
T.
Time. T is time.
So example,
Force.
absorbing surface.
Sorry.
Example of absorbing surface.
Black body is a surface which absorbs radiations. Your wall is a good absorber. It absorbs your radiation. But if you take a mirror or a polished surface, then that is a reflecting surface.
Okay, sir.
And the last definition is intensity. Intensity of EM wave. So intensity of EM wave is nothing but intensity is energy per unit area per unit time. Energy divided by area divided by time is the intensity of EM wave. Fatma, tell me, what should be the SI unit of intensity? What is the SI unit of energy, Fatma? SI unit of energy, Fatma.
Joule.
Joule. SI unit of area,
Meter.
meter square.
Mhm.
Time,
Second.
second. So that's joule per second per meter square. And what is joule seconds? Joules per second. That's watt, right?
What?
Watt per meter square. So that's the SI unit of intensity. Note it down. We'll do a few numericals now. Written?
Yes, sir.
Sure. Intensity is over, momentum is over. Okay, let's do this numerical. Just write this numerical, then we'll solve it. Just note it down.
Sir, NCRT numerical.
Yes, this is from NCRT. Written?
No, sir.
Okay, can you tell me what is this term? 18 watt per centimeter square? Is this
Intensity.
is this energy? Is this power, intensity? What is this?
Intensity.
Intensity, right? It's 18 watt per centimeter. Huh? We just have written the unit of intensity, watt per meter square. So this is the semi-CGS unit, watt per centimeter square. Intensity is given. 18 watt per centimeter square. Now, can you convert centimeter into meter? 1 centimeter square is 10 raised to the power minus 4 meter square. So you can write this as it's 18 into 10 raised to the power 4 watt per meter square. Watt per meter square. So that's intensity. 18 into 10 raised power 4 watts per meter square is the intensity. The area is 20 centimeter square. So you can write this as 20 into 10 raised to the power minus 4 meter square. time is given as 30 minutes. Or you can say that time is 30 into 60 seconds. So if you have intensity, you have area, you have time, can you calculate total energy?
Yes, sir.
Ahmed, can you think of a relation between intensity, total energy, area, and time? Ahmed,
Yes, sir.
and what that relation is?
Area by like energy by area time.
Energy by area by time is intensity. So how much is energy here?
So we have to find that idea.
So we can calculate energy, right?
Yes, sir.
So I can write energy as U. It's my choice now. Let's use U for energy. That's U. So intensity is 18 into 10 raised to the power 4. Area is 20 into 10 raised to the power minus 4. Time is 30 into 60. This much of joule is your energy. And what type of surface is this? Is it a reflecting surface or a non-reflecting surface, Fatma? Surface is reflecting or non-reflecting?
Non-reflecting.
Non-reflecting. So can you think of an expression for force?
2p by t.
For a non-reflecting surface, it's 2p by t.
P by t.
P by t. So, and how much is P? What's the expression for momentum?
I didn't get you, sir.
Just to remember. What is the expression of momentum, Fatma? We just have done, huh? Expression of momentum for an EM wave. Okay. Sania, will you tell expression for momentum of EM wave? Okay, Abdullah. Sania, do you remember any expression for momentum of EM wave?
No, sir.
No. See, you just have it. This is the expression. This is momentum, huh?
Yes, yes.
So the momentum carried by EM wave is total energy of EM wave divided by speed of light. So this is energy of EM wave, 18 into 10 raised power 4. We can solve it. So that is 18 into 20, 10 raised power 4 into, not 4. 18 into 10 raised power 4 minus 4. So that's 18 into 20 into 10 raised power 4 minus 4 will be 0. And then you have 30 into 60 divided by speed of light, which is 3 into 10 raised to the power 8. Now, this 3 will cancel this 18, it's 6. And the momentum carried by EM wave is, it's 120 into 30 into 60 over 10 raised to the power 8. This is the momentum carried by you. So once you have momentum, you can calculate force. Huh? What's the expression for force, Shahzada? So Shahzada, now we have momentum. What's the expression for force exerted by EM wave? Shahzada, can you remember any expression for force by EM wave?
So force is
See, just check your notes. Huh? Somewhere we have written expression for force. This is force, right? So this is expression for force, P by T or 2P by T. So which expression you will use in this numerical, P by T or 2P by T, Shahzada?
so P by T.
P by T is a non-reflecting surface, it's absorbing surface. So force will be P by T. So P is 120 into 30 into 60 over 10 raised to the power 8. How much is time, Shazada? Time is giving somewhere. How much is time? Yes, Shazada, how much is time? It should be given somewhere. Just read the question. How much time is given? $30. Nah? See, it's given here during the 30-minute time span. So it's 30 into 60. 30 will cancel this 30, 60 will cancel this 60. So force comes out to be 120 into 10 raised to the power minus 8. So this is the force acting or force applied by this thing. This is the applied force. 120 into 10 raised power minus 8. Note it down, please. You all have written the question, na?
Yes, sir.
Ahmad, it won't be 2p by t. 2p by t is for a reflecting surface. It's a non-reflecting surface.
Yes, sir.
And please don't copy this numerical. Do it yourself. If you stick somewhere, just ask. Haji, written?
जी सर.
Sure. So this is about this intensity and energy thing. The last is the electromagnetic spectrum. Majority of the question in electromagnetic waves are on this spectrum. I'm just drawing it. The last topic is electromagnetic spectrum. See, the electromagnetic wave that we just read have several examples. There are various types of electromagnetic waves. The one is gamma rays, example of electromagnetic waves. Another is X-rays, is again an example of electromagnetic waves. Ultraviolet, visible light, visible means this violet to red colors, infrared, microwaves, radio waves. These all are examples of electromagnetic waves. And this whole spectrum, right, starting from the gamma rays to the long radio waves is known as the spectrum of electromagnetic waves. Majority of question in electromagnetic waves are from this spectrum. So see what type of question you can get on this spectrum. The first type of question that can be asked from this spectrum is the frequency range of EM wave. Like you can ask, what is the range of X-rays, frequency range of X-rays? So X-rays can lie from 10 raised power 20 to 10 raised power 16. That's the frequency range. Someone can ask the wavelength range of X-rays. So that's 10 raised power minus 12 to 10 raised power minus 8. Similarly for infrared, similarly for microwave, short radio waves. So from this electromagnetic spectrum, you have to remember three things. First thing, frequency range. First thing is frequency range. Second thing is wavelength range. Third, frequency range, wavelength range, and the third one is uses of EM wave. Like you should remember the uses of X-rays, uses of gamma rays, uses of ultraviolet rays. And the last one is mode of production. How will you produce X-rays? How will you produce gamma rays? This is what you will do from NCERT. Like I can't help you in it. You yourself have to remember the frequency range. Yes, no, you have to read by heart. The questions that we get, one can get from the EM spectrum is like he will tell you there is a wave which have a frequency of 10 raised power 17 hertz. Just name that wave. Write the wavelength range of the same wave and also the frequency, uses and mode of reproduction. So these are the type of questions that one can get from this electromagnetic spectrum. Once there was a question, there is a wave which is used to see bones. That's an X-rays. Right is frequency range, its wavelength range, and the mode of production. How will you produce this X-rays? Mode of production. So for each and every wave, you will remember these things. Don't write this spectrum, just note down the topic, electromagnetic spectrum, and these points. Right? You have to remember frequency range, wavelength range, uses, and mode of production. Yes, can I change the slide now?
Yes.
Okay. So electromagnetic waves is over. This was the last topic